Hello everybody, so in this video we're going to start with chapter 3, sequences and series. So here we have the learning objectives for this chapter, and by the end of this chapter you should be familiar with working with arithmetic and geometric sequences, finding the sum of finite arithmetic and geometric sequences, and finding the sum of infinite geometric series using sigma notation, using the binomial theorem for the expansion of a plus b to the n, with n belonging to the natural numbers. Working with counting principles, including permutations and combinations. So let's start with section 3.1, sequences. And here we can see some figures that represent triangles that are ever increasing. So this is one kind of sequence, as we can see here. So notice that the first term is 1. So this represents a sub 1 represents the first term, and this one is the index. Notice that the second term is going to be 3, then the third term will be 6, then the fourth term is 10, the fifth term is 15, and the sixth term is 21. So notice that if a sub n is the nth term of a sequence, then a sub n minus 1 is the term before it, and a sub n plus 1 would obviously be the term after. So this sequence that we see here is one called a recursive sequence. It's a type of recursive sequence. Now notice that what we can do here to find the nth term, we could define the nth term as equal to the previous term plus whatever n is. So notice that, for example, the third term is equal to the second term plus the index, which in this case would be 3. So the third term is equal to the previous term, which is 3, plus the index that we have for the third term, which happens to be 3 as well, and this is 6, as we saw here. Okay, so next we have example 3.1, and it says find the first 5 terms and the 50th term of the sequence b sub n, such that b sub n is equal to 2 minus 1 over n squared. Notice that we are given an explicit expression for the nth term, as we can see here, as a function of its term number, n. So n is the term number, and all we have to do is just find the value of the function for the required term. So notice that for the first term, we would have 2 minus 1 over 1 squared, and this is simply going to equal 1. For the second term, we would have 2 minus 1 over 2 squared, and this is going to give us 1 3/4. For the third term, we're going to get 2 minus 1 over 3 squared, and this is going to give us 1 8/9. The fourth term is going to be 2 minus 1 over 4 squared, and this is going to be 1 15/16. So notice that we get a pattern, right? The fifth term, so the fifth term is going to equal 2 minus 1 over 5 squared, and this is going to be 1 24/25. So you can guess what the 50th term would be, right? The 50th term would be 2 minus 1 over 50 squared, and this is going to be 1 2,499 over 2,500. Very well, so next we're going to do example 3.2, and it says find the first 5 terms and the 20th term of the sequence b sub n such that the first term is equal to 5 and the nth term is equal to 2 times the previous term plus 3. Okay, so this type of sequence that we have here is what's called recursive. It's recursive because we require of the previous term to find the next term. So the first term is already given to us. They tell us that it is 5. So that means that the second term is going to equal 2 times the previous term, which would be 5 plus 3. So this is going to give us 16. The third term would then be 2 times 16, the previous term, plus 3, and this is going to give us 38. The fourth term, again, 2 times the previous term plus 3, and this is going to equal 82. And then the fifth term, same thing, 2 times 82 plus 3, and this is going to be 170. But notice that they want us to find the 20th term. So is there a quick way of finding the 20th term? Well, no. We would require the 19th term, which means that we would have to continue doing the same process. So in order to solve this problem, we're going to use the graphing display calculator. Okay, so here we are with the graphing display calculator, and we're going to find the 20th term of the recursive sequence, right? So the first thing you have to do is go to mode, and you're going to have to go down to where it says function and change that into what it says SEQ for sequence. So let's hit enter there. And then we go second key and quit to get out of there. And let's go to y equals. And notice that here we have everything ready to plug in our sequence. So that first thing you see there, which says n minimum is equal to 1, that's fine. We can leave it like that. And then next, we have to plug in the function. So it's u as a function of n. So that means that u is the term and n is the index. So remember that we said that the formula is 2 times, we want to write that, all we need is a parenthesis, so 2 times the previous term, right? So how do we write the previous term? Well, we would use u, which you can find when you do second key and 7, and then you use parenthesis, and you type in n from here, from the normal variable, minus 1. So we don't have index notation, but the calculator understands that this is the previous term of u. So the previous term plus 3. And then here we close parenthesis. So next, what we have to do in this case is introduce the first term, which we said is 5. To look at the table, we go second key and graph, and there we are. So for the 0, it always gives an error, but that's okay, no problem. So notice that we have the first term, which is 5, and then 16, 38, 82, and 170. Those were the terms that we found previously. But we want to find the 20th term. So what can we do to find the 20th term? For that, we need to go to second key and table set. And notice that it has several things there, but we're not interested in anything there. Don't change anything except where it says independent, auto or ask. So that's the independent variable, ask for the independent variable. So let's set it up like that, hit enter there. And now let's go back to the table. And notice that it says n equals, meaning that it's asking for the term we want. So then we would type 20 and click on enter. But we want to look at the number specifically. So let's highlight the number, and there it is. Notice that it's actually a large number, right? It's 5,767,162. Okay, so here we are in example 3.3, and it says a Fibonacci sequence is defined recursively as the nth term is 1 for the first term, 1 for the second term, and then the previous two terms added for any term greater than 2. And let's recall that the first 10 terms, which is part A, find the first 10 terms of the sequence, would be 1, 1. Then we add these, it gives us 2. Then we go 2 plus 1, that would be 3. 3 plus 2, 5. 5 plus 3, 8. 8 plus 5, 13. 13 plus 8, 21. 21 plus 13, 34. And 34 plus 21, 55. So these would be the first 10 terms of the Fibonacci sequence. I'm going to explain how to use the graphing display calculator to generate the Fibonacci sequence. Okay, so here we are with the GDC, and we're going to generate the Fibonacci sequence. So recall that we go to y equals once we set up the calculator to do sequences, and here we have to plug in the formula, right? So remember that the Fibonacci sequence is the sum of the previous two terms. So in terms of u, we would have to say second key and 7 for the u. So it would be u sub n minus 1, which would be the previous term. So n minus 1 would be the term before n, and then this plus u, so second and 7, and now the index is going to be n minus 2. So that's how we would get each term in the sequence. But it's very important to put in the first two terms, which are 1 and 1. And once we have this, all we have to do is hit on the second key and then table, which is above graph, and there it is. Notice that we get an error for 0. That's normal. But notice that the first term is 1. 1 is the second term. 2, 3, 5, 8, 13, 21, 34, and 55. So we've generated the first 10 terms of the sequence. The advantage of the calculator is that we could find out what is, for example, the 1,000,000th term. We're not going to do that exercise here, but if you want to experiment, you can check it out for yourselves. So for part B, they want us to find the sum of the first 10 terms of the sequence. So that would be the same as adding all these numbers, and that is symbolized as the sum of the first 10 terms of the sequence. We will get to that in a minute. But I want to do the sum of all the terms, and notice that it's going to be an interesting thing here. So look, the sum of the first term is just going to be 1, so that's this. The sum of the first two terms is going to be this number plus the next number, so that's going to be 2. Okay, so the sum of the first three terms is going to be this plus the next term, so 4. The sum of the first four terms is this number plus this number, so 7. The sum of the first 5 terms is going to be 7 plus this number, so that's going to be 12. The sum of the first 6 terms is going to be 12 plus 8, therefore 20. Then the sum of the first 7 terms is going to be 20 plus the next term, 13, so 33. The sum of the first 8 numbers is going to be 33 plus the next term, which is 21, so we're going to get 54. The sum of the first 9 terms is going to be now 54 plus 34, and we're going to get 88. And then finally, the sum of the first 10 terms will be 88 plus 55, and that's 143. Okay, so now I'm going to show you how to create a Fibonacci sequence using an Excel spreadsheet. So we would type in, notice that I have 2 columns. I'm going to use columns A and B, and this represents each term. So the first term is 1, the second term is 1, and then every subsequent term is the sum of the previous two terms. So notice that I can say that this here is equal, and we use parenthesis, to A2 plus A3. And then we hit on enter, and there we get 2. Now what we have to do is just copy this, and then we can paste it down this column, and notice that we generate the Fibonacci sequence: 1, 1, 2, 3, 5, 8, 13, 21, 34, 55, 89, and so forth. Okay, now we want to generate the sum, the nth sum. So remember that the first sum was 1, and the second sum was this plus this, so 2. Okay, so now let's generate the sum automatically. So notice that it's going to be the sum of the previous two terms, which is B3, plus the next term, which is A4. So we can just write here, let's make this equal to, we put parenthesis, and we said B3 plus A4. Just hit on enter, and there we go. We get 4, which was correct, right? Now let's copy this, and let's paste it down here, and there we go. So notice that we generate the sum of the terms. So this would be the sum of the nth term. So notice that we get 143, which is something we had found before. And then if we had to do the subsequent sums, here they are as well. So for part C, it says, by observing that the first term equals the third term minus the second term term equals the fourth term minus the third term, and so on, derive a formula for the sum of the first n Fibonacci numbers. Okay, so first let's verify this. So notice that the sequence again is 1, 1, and then 2, and then 3, and then 5, and then 8, and so forth, right? 13, so forth. So let's identify. This is the first term, this is the second term, this is the third term, this is the fourth term, this is the fifth term, and this is the sixth term. So remember that we can say then, normally, right, we know that the third term is equal to the sum of the second term plus the first term. So that implies that the first term is equal to the third term minus the second term, obviously, and so forth, right? So how can we derive a formula? Let's look at a pattern here. So we know that the first term is equal to third term minus the second term. And we know that the second term is going to be the fourth term minus the third term. And then we have that the third term is equal to the fifth term minus the fourth term. And then we have that the fourth term is equal to the sixth term minus the fifth term. And then if we continue with the same pattern, what are we going to get? Well, notice that this means that the nth term is equal to two terms after the nth term minus the term following the nth term would give us the nth term. Okay, but they want us to derive, it says, a formula for the sum. So we can derive that by adding all this, right? So this column here, we can call the sum, the nth sum, would then equal f of n plus 2, right, as the index, two terms after the term we're checking. This would be the term. So notice that then if we add all these, this will cancel out with this, this will cancel out with this, this will cancel out with this, and this will cancel out with the next one, and so forth. we're only going to be left with the last one, which we have here. And then what's going to happen is that this is going to cancel out as well. So what are we left with? Well, we're only left with this. So this would be the formula that would give us the sum for the first n Fibonacci numbers.